video we'll discuss our star, the sun. The sun is larger compared to Earth. In fact, it's much larger. It's enormous. The surface temperature of the sun is about 5,500 degrees Celsius. You can find this on page 15 of your reference table. And remember, on page 15 of our reference table, the temperature goes with the color. So our sun's color is technically yellow if we're using that chart. The interior, however, is even hotter. And remember, on the inside of a star, we believe that nuclear fusion is occurring, and that nuclear fusion is how stars get their energy. Pause the video so that you can fill in your diagram of these layers. Let's start with the explanation of the corona. If we want to look at this whole cross-section of the sun, we have to think this is not just the interior, but it's also the outside layers as well. So the corona itself is the outermost gaseous layer of the sun. Next, as we move towards the inside, this would be the chromosphere. Chromosphere, again, a gaseous layer that we would find on the outside. You finally get to the surface of the sun when you get to the photosphere. Below the surface now, we have the convection zone and the radiative zone, and then all the way in the center is the core. And again, in the core, we believe nuclear fusion is occurring, which gives the sun and all stars their energy. Sunspots are the first piece of the sun that we're going to talk about today. Sunspots are dark spots that are on the photosphere. When you look at that picture, it's really zoomed in, so you might think that looks kind of strange. But what's really neat about sunspots, and kind of goes back to the very first thing I said in the video, is that a sunspot could be even larger than the size of planet Earth. So that just gives you an idea of how enormous the sun is compared to our planet. But these dark spots on the photosphere, or dark spots on the surface, have intense magnetic activity. They're cooler than surrounding areas on the sun. They sometimes appear in pairs. And really important piece is that they move from left to right across the sun's photosphere, the sun's surface. What's interesting about that is astronomers observed the movement here across the surface of these sunspots, and they realized from that observation that the sun must be rotating. So sunspots really led us to believe that yes, the sun does rotate. Also, sunspots, they have a different amount that we're going to see from time to time. The peak activity is about 100 that we'll see on the surface, and the low activity is we can go days without seeing any. But we found that there is a specific cycle that these sunspots go through, and it's about an 11-year period from peak to peak. So if you remember the relationships that we've talked about, this goes in cycles, okay? So if you can think about what that graph would look like, it would have kind of look like that wave. It would have the high peaks and then the lows. Solar flares actually are eruptions that come out of sunspots. So because a sunspot has intense magnetic energy, a solar flare is also going to have magnetic energy within it. And this is released through the atmosphere. Radiation is emitted across virtually the entire electromagnetic spectrum. Solar flares are the most energetic explosions in our solar system. But if you think about our solar system, our sun is the only star, so it kind of makes sense that that would be true. Solar flares have a direct effect on the Earth's atmosphere. The intense radiation from a solar flare travels to Earth in 8 minutes, which is super fast. And as a result, the Earth's upper atmosphere becomes more ionized and expands. Long-distance radio signals can be disrupted by the resulting change in the Earth's ionosphere. A satellite around the Earth could be disrupted, or it could be damaged. So yes, solar flares do have an impact on some of the technology that we use here on planet Earth. But as far as your life day to day, solar flares don't really disrupt it that much. So here's a picture to kind of help you understand how big the sun actually is and what a solar flare might look like. So if you look at the picture, you can see this is just a small section of the sun. here's your solar flare, and then here is what we would assume Earth to be if we put it right up next to the sun. So you can see the sun truly is enormous compared to our planet Earth. Last thing we want to talk about is the solar wind. The solar wind streams off of the sun in all directions, and it can go at speeds of 400 kilometers per second, which is about 1 million miles per hour. So it's super fast. The source of the solar wind is the sun's hot corona. Remember, that's that outer piece of the sun, that gaseous layer, which in this picture right here would be like this outside section right here. The temperature of the corona is so high that the sun's gravity cannot hold on to it, and it is released there in the solar wind. So the solar wind has charged ions within it, and those ions are sent out to planet Earth. Planet Earth has a magnetic field around it, and that's what protects us from things like the solar wind out in space. Those ions, though, are attracted to the magnetic poles of Earth, just like iron filings are attracted to a bar magnet, if you've ever seen that demonstration. So these charged particles will move towards Earth. They'll be attracted to the north and south magnetic pole. Once they get there, they interact with Earth's magnetic field, so they get really excited. They're moving around very quickly, and the result of that is in the form of light. So what we see the solar wind producing is the auroras, or the aurora borealis, or the northern lights. So once again, Earth's magnetic field shields us from that solar wind, which is all those charged particles. As the solar wind reaches our magnetic field, the particles will interact with our magnetic field in our upper atmosphere, and that causes light. And this is a very common event near Earth's poles, because they're near the magnetic pole where these ions are being attracted to. Here in the lower portion of New York State, we really don't see the auroras at all, but upper parts of New York State does get to see this. Parts of Canada, Alaska, Maine, higher latitudes are definitely going to be able to see this from time to time. So just to give you an idea of what this looks like, if we just do a quick Google search of the northern lights or the auroras, this is what we come up with. Now these pictures, first glance, kind of look fake, but this is actually what will happen in the sky. You'll see these bands of colors that are produced. They kind of move around. I've personally never seen them, but it must be an amazing sight to see. So again, these are caused or formed by the solar wind interacting with our Earth's magnetic field to produce light.